Okay.
Yeah,
Cool.
the speaker is Yushwan Wang from Michigan, and we'll be talking about overdamped phonon dynamics.
Yeah, thanks so much. Thank you so much for your introduction. So, hi, my name is Yushan. Today, I'm going to talk about efficient first principles framework for overdamped phonon dynamics and our harmonic electron phonon coupling in superionic materials. Put this up a little bit. Can you hear me better? Okay. All right, so there has been one question that's been troubling the material science community for a while. That is, why does copper-2 selenium has such a good thermoelectric coefficient, right? And since we're talking about material, let's bring down the crystal structure, sorry. So you can see here up top, we have a low temperature structure, which is monoclinic, and then we go down, which we increase temperature to 414 Kelvin, you have the cubic structure. And since we're talking about the thermoelectrics, let's bring out the ZT value. So in order to evaluate how good this material is, on top we have the Seebeck coefficient and the electronic conductivity. So that's the electronic part. And on the bottom we have the phonon part, which is the thermal conductivity. And so in order for us to explain why this material is so good, we should be able to explain two sides of the equation. So both the electronic part as well as the phonon properties. So one thing is at least calculate their band structures correctly, electronically, as well as the phonon bank structure, right? And so the first myth is that does copper actually occupy high symmetry positions? Because people previously tried to calculate the high symmetry structure they believe to be existing at high temperatures, and then they found that even like across the board with different functionals, you can see it has zero value or severely underestimates the band gap value. Even when you use PB plus U, that's actually a physically large U value of 10 eV. And so the takeaway here is, oops, sorry, is this going up? Okay, yeah. So all calculations for the high symmetry structure essentially underestimate severely this experimental gap. And so why is this? Well, there might be superionic copper vibrations that's going on. And so copper atoms in this structure actually vibrates a lot more than a typical atom. So actually it vibrates in this tetrahedron region in amount about 0.46 angstroms, which is much larger than a typical material like your silicon and gallium arsenide. And what this causes is that if I plot the potential energy surface with respect to nuclear displacement, you can see on the top we don't have this harmonic well anymore. We start having aharmonicity, essentially distortions in your nuclear potential. And what this can cause is, because the thermodynamics average observable on the left cannot be accurately reflected by just calculating the average structure, so the average high symmetry structure, that's calculated by Zunger and collaborators. And thus we start to bring up our hypothesis, thus how does structure affect the phonons as well as the electrons, right? So in this work, we set off to study, first of all, at 0 Kelvin, whether there are any symmetry breaking and 0-point motion effects. We call this ground state disorder. And moving on, at higher temperatures, we essentially include temperature effects. So phonon frequency corrections, as well as electron phonon coupling. We call this anharmonic vibrations in this work. And which of those are more important, right? And there lacks actually a method to account for this really well, because previously people mostly use molecular dynamics. Well, with that, you couldn't really decouple those two. You couldn't really decouple those two. And also, generally, you take a lot of snapshots through time. I mean, it can be helped with molecular machine learning, sorry, but still, with this method, which is a special displacement method developed by Zacharias and Justino, you can actually take one single snapshot, essentially one unit cell, to do the calculation. It's a non-perturbative method that's able to capture both the harmonic as well as the anharmonic electron phonon coupling to all orders. So it's very impressive. And essentially we'll apply the special displacement method. So here, we discuss our methods, PBE functional to calculate the phonon dispersion on the order structure. And then moving on, we can apply harmonic approximations using the harmonic version of the special displacement method, do a relaxation on top of the, essentially following the soft phonon modes, and get the disordered ground state. And at the end, we apply the harmonicity, essentially, corrections. So at each and every single finite temperature, we get a different structure, and we feed those structures into VASP to do a more accurate HSE calculation for the electronic band structure. So some of the results. So first thing is that the effects on the electronic band structure. So on the left here, I show essentially in blue the high symmetry structure. So unperturbed coppers, everything's looking symmetric. And then at the background, the red, I have the disordered. So you can see here, even though the ordered structure don't have a band gap, the disordered actually not only has a band gap, but also has many different values across the Bouillon zone, which can increase the Seebeck coefficient. Yeah, it helps to explain the thermoelectric performance of this material. And on the right, I plot the band gap with respect to temperature. So if you use the high symmetry structure, as people will previously have done, in the ordered structure, if you only ordered including temperature effect, this gives you a band gap opening. However, when we use the disordered structure, you can see from the left, even at 0 Kelvin, this is a 0 Kelvin figure, you can see there's a 0.85 eV gap opening. But if we further apply temperature on top of that, we get actually a band gap closing, which is very interesting, in contrary to what people have found before. And so because people generally measure copper 1.9 selenium, they introduce a little bit of copper vacancy just to stabilize the structure at room temperature to do band gap measurements. We should account for this copper deficiency because we previously calculated copper 2 selenium. So how do we do that? We use something called the bursting Moss shift. So what this does is that you can imagine this copper deficiency, essentially what it does is that it empties some of those states at the top of the valence band. So we essentially just need to calculate essentially how many states it empties and what kind of gap opening or energy lowering in terms of the Fermi surface that corresponds to be able to get this 0.26 eV value, which added up to be 1.11 eV for the copper 1.9 selenium prediction at 0 Kelvin, which is in excellent agreement with experiments. So we add this on our plot. And this gap, again, closes with temperature if we compare it to experimental results. And so what's the key takeaway here is that the ground state disorder is actually much more important than the anharmonic effects. Okay? And next, I want to go over the phonon dispersions. So yeah. So here, essentially, on the blue, we plot the order structure, high symmetry, including anharmonicity, so temperature effects. And then on the background, we plot the disordered figure. So what you can see here is that on the right, this is the integrated, essentially, partial density of state for the phonons. So what you can see here is that if we only look at the blue lines, so that's the high symmetry with only temperature effects, you can see the density of state actually has very distinct sharp peaks. That's not observed in the experimental data, which is lying on the bottom here. And you can see from the figure on the left that it's like the high symmetry structure has a lot of distinct bands, while if we actually include disorders in our structure, this is at 430 Kelvin, you can see that the bands actually smear out a lot more. So our takeaway from here is that, okay, when we include actually the disorder, when we do the density of state again, it's actually very nicely agreeing with experimental data. So the first thing that we conclude from here is that local copper ion diffusion actually differs from the quasi-particle band theory. Essentially, your band get very smeared out from this very symmetric quasi-particle picture. And this leads to strongly correlated vibrations with finite phonon lifetimes and essentially lowers your thermal conductivity to give you a good thermoelectric coefficient. And essentially the key takeaway is that local disorder is the key to accurate phonons as well. So here I conclude my talk. Essentially, we developed a very efficient framework for copper-based superionic materials and found that local disorder as the key to superior electronic as well as phononic properties instead of anharmonic effects. And this is a link if you want to see our paper. And this is submitted to PRL. And thanks for any referees if they're in attendance today. And we'd like to thank University of Michigan, NSF, AXEX, NERSC, and EPW for their funding and support. Thank you very much.
Sorry, maybe I misunderstood a bit, but I'd like you to restate again, what do you mean exactly by local disorder? Do you mean the change in the electronic band structure? Please clarify.
Oh, okay, yes. So essentially let me see, I can go probably quicker from here. So essentially the disorder that's, okay, let me see, I need to present again. Essentially the disorder that's shown here, right? This has like, essentially, you know that copper actually diffuses a lot. There's like nearest neighbor hopping, and then the next nearest hopping, and then there's even the third nearest neighbor hopping. So essentially, this picture shows ordered and disordered, right? So, but the reason why we say local disorder is that by Voneshin and collaborators' experimental work, they found out that actually the second and the third nearest neighbor, essentially above first nearest neighbor, like copper diffusions, they don't contribute to the lowering of the thermal conductivity. So that's why we include the local term here. That's essentially where the local comes from. Yeah, sorry, I didn't have time to go into that detail because it's a short talk, but yeah, that's a good question.
Thank you.
Yeah.
Thank you for the great talk. I could be totally wrong because of the projector resolution.
Yeah, go ahead.
But for your spectral phonon band structure, I think I saw some negative modes. I'm not sure if I'm right, but if that's the case, do you know what is the origin of those negative modes?
I think I don't think we observed any negative modes. So if we only use if we don't use the special displacement method, we do see negative modes because the cubic structure is not stable at the temperature above 414 Kelvin. But since we account for the anharmonicity in this case with the special displacement method, it actually eliminates all the negative modes. Yeah, I have a picture, but maybe I don't have time to show. Yeah, is that time for me? Yeah. Okay. Yeah. Thanks.